All right, time is 4 o'clock, so let's get started. And first of all, I guess good afternoon, everyone, and welcome to this talk on how to apply the principles of chaos engineering to serverless. We're going to spend a few minutes to talk about what is chaos engineering and what it is not, and some of the new challenges that the serverless paradigm has presented to the current set of tools and practices that we have for doing chaos engineering, and how we may be able to tweak some of these current practices to make them work for serverless. Technology. So after the talk, all the slides are going to be available on SlideShare, and the recording will be published on the YouTube within 48 hours, and you can find links to both on my blog as well. Okay, click us out. So let's start with what is chaos engineering. If you go to principlesofchaos.org, you'll find this nice definition that says chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. Now, that sounds great, and it talks about distributed systems, and it talks about building confidence. But personally, I still find it to be quite vague in terms of what do we actually do in practice. Personally, I like to use analogies, and I think the perfect analogy for chaos engineering is vaccination. And you can't talk about vaccination without going all the way back to smallpox, which was easily one of the most deadly diseases that we have ever encountered as a species. And it was killing people in the hundreds of thousands every year in Europe alone, until about 1798, when Edward Jenner created the first vaccination. And less than 200 years later, we were able to eradicate smallpox at a global scale. Today, we have over 25 different vaccinations for different infectious diseases, and in the UK, by the time you're 14, you would have had at least 20 vaccinations already. And vaccinations has become our most effective defense against infectious diseases, and it works by injecting ourselves with a very small dose of the disease, not enough to make us sick or anything, but enough to trigger our body's autoimmune system to start identifying this foreign agent as danger and to start building defense against it before we actually come into full contact with the disease. And I think that's where we can draw a lot of parallels with chaos engineering, whereby we are using controlled experiments in order to inject failures into the system deliberately so that we can learn about how the system fails under those failure conditions before they actually happens in production in an uncontrolled fashion. So now we still have the time to understand how the system behaves and then to go back and build our systems to be more resilient, to harden our application against those failures. And in time, as we repeat this process and iteratively harden our application against different forms of failures, we can also start to build confidence that our system will actually be fine in production regardless what turbulent conditions it's going to face. So I think it's fair to say that chaos engineering is the vaccine for frailties in modern software, which tend to be A, distributed, and B, runs in the cloud. So my name is Yan Cui. I'm a principal engineer at DAZN, and as of July this year, I'm also one of the AWS community heroes that focuses on the serverless space. I'm also the author for the production-ready serverless video course by Manning, where I share a lot of the lessons that I've learned by running and operating Lambda and serverless architectures in production. And in my spare time, I'm also a very active blogger, and I go to many conferences and user groups to talk about many of the things that I've learned about serverless. So DAZN is a sports streaming platform. We have a monthly subscription fee like Netflix, except you're not streaming movies, you're streaming live sporting events instead, and of which we have over 40 different sports and over 200 different leagues all around the world. And we have recently launched in the US, and we are streaming boxing matches now. In total, we are available in 7 different countries and over 30 different devices. And at peak, we have around 1 million concurrent viewers for any given sporting event that we are streaming. And because everything we stream are live, and we can't just turn around to our customers and say, sorry guys, we're down. Please come back in half an hour when your event has finished. So that clearly is not going to fly with anybody, which is why resiliency is very high up on the list of priorities for us. And given that application runs in both containers and Lambda functions, and given my personal interest in the serverless space, I spent a lot of time thinking about how can I take some of these current practices that we have with chaos engineering that doesn't quite work with serverless just yet and make them work and use them to help me make my serverless application more resilient. So before we go into that, I also want to share with you some of my observations about this space of chaos engineering, whereby often when I try to read about what other people are doing, I'm seeing blog posts with titles like breaking things on purpose, the joy of destruction, which worries me a lot because it just puts so much emphasis on breaking something and nothing about why we're doing it. Our goal is not to actually end up with a broken system in production. It's the opposite. We want systems running in production that are resilient, that can stay up even when bad things happen. And when you put so much emphasis on the action of injecting failures, it's easy to conflate them with the outcome that you're hoping to achieve. The point is to learn how your system fails before they actually happen in production, so that now you still have the chance to make your system better, to put in the engineering effort to harden your system against those failures. And in time, by doing this, you can repeatedly doing this, you can start to build confidence that your system will actually be fine. And even if we are intentionally breaking things in order to learn how our systems fails, breaking things itself is not the goal. Again, if you go back to principlesofchaos.org, which is generally one of the best places you can go to learn about chaos engineering, it outlines 4 simple steps that any one of us can follow to start doing chaos experiments ourselves. Step 1, we need to know what normal actually looks like for our system. What does normal working condition looks like? But if everything's on fire all the time and you're constantly firefighting and every day you come in, the different kind of problem is breaking things, then I'm afraid you don't have a steady state. And you're not ready to start doing chaos experiments for the same reason that you wouldn't vaccinate someone if you know their immune system is already broken. And vaccination is just going to do them more harm than good. But if you're one of the lucky ones, and you do have a working system, and you know what your steady state looks like, then now you can start to design scenarios and hypothesize, given some failure happens in the system somewhere, how is my system going to behave? And here you want to explore all kinds of different scenarios, including scenarios where you just have no idea what the hell is going to happen, how your system is going to behave. And those kind of scenarios are great for learning and finding weaknesses in your system very, very quickly. But given that you don't actually know what's going to happen, maybe you don't want to go straight to production with those kind of experiments for good reason, right? And experiments that actually graduate all the way to production, they need to be carefully considered, planned, and carefully executed. And by the time you hit production, you should have a very good confidence that your system is actually going to be fine. It's going to be able to handle the failure properly. And you only get there based on the knowledge that you're able to gain, the understanding about a system that you're able to gain by running those experiments in an environment outside of production where the stakes are not so high. So run your experiments in dev environment, in staging, run your experiments in dev and staging where you can try out all these scenarios that are potentially risky, that you don't want to do them in production right away, where you can learn so much about how your system behaves. Just as the goal of vaccination is not to actually catch a disease, the goal of doing a chaos experiment is not to actually hurt your production environment either. And if you know your system is going to break and you do it in production anyway, then that's not what we call a chaos experiment at all. For one, you haven't learned anything you didn't know before doing that. You knew it was going to break and you broke. Congratulations, you learned nothing. Well, hopefully you learn not to do it again. All you would have done in that case would have just angered your users and damaged your reputation and your brand. So please do not make that very, very silly mistake. And the next step would be to actually then go ahead and inject some failures into your system. And this is where Netflix's Simian Army is a great tool for doing that, especially if your application runs on VMs or runs on containers, perhaps. And the engineers at Netflix also publish a free ebook that you can download from O'Reilly using this link, where it talks about how the engineers at Netflix, how they run game days where everyone gathers together to brainstorm how the system might fail under different failure conditions, and what kind of experiments they can design. And he also talks about the process by which they communicate with each other in terms of what experiments are going to happen, what they're going to test, and then how they go about planning and executing those experiments as well. So whilst running your experiment, you're keeping an eye on the dashboard to make sure that at the top level at least, there's nothing really, really bad happening. And if there is, then stop the experiment right away. And afterwards, you go through your metrics in more detail and try to look for evidence whether or not your steady state was impacted by the failure that you injected. And if you are able to find a weakness, great. Something failed they didn't expect. Now is the time to go ahead and fix it before it actually happens for real. And since the goal is not to actually hurt production, we need to make sure the experiments that we are running are actually done in a controlled manner, and which is why containment and blast radius should be front and center of your thinking at all times, especially if you want to move your experiment into the production environment. The point, again, is not to actually hurt production. So how do we actually keep those experiments under control? I think one of the most important things you need to do is make sure that everybody involved is communicated so that if your experiment can potentially impact the systems owned by a different team, make sure that they are aware of what you're doing and that they're okay and they're ready for it. It should never be a surprise to somebody else that, well, your experiments end up hurting their systems. So I shouldn't have to come into the office one day, look at my dashboard, and everything's red. And by the time I spend hours investigating what the hell is going on, it turns out, wait a minute, you guys are running some experiment, and that's why all my systems are broken. Well, it's great. Now that we've identified some cascade failures, we can go back and fix it, but maybe you should have told me in the first place so that I know what to look out for, as opposed to waste all this time trying to dig around and see what's going on. And you also want to make sure that you run your experiments during office hours when people are in, they are in front of laptops, and they're ready to deal with any unexpected fallout. And if you have important launch dates coming up, for example, if you have Netflix and you're launching the new Narcos Mexico's TV show, which is great, by the way. Binge it if you haven't already. I've done my share already, spent so much time watching it last week. It's amazing. Or in the case of DAZN, if a boxing match is about to happen, then avoid those important days, important times at all costs. You don't want to go to production and take unnecessary risk and taking down system when there's something really important is happening. There's a time for taking risk for the sake of learning, but then there's also time for good old common sense and not take any unnecessary risk that you don't have to. You also want to make sure that you make the smallest change possible that still allows you to detect and decide and prove your hypothesis, but not risk entirely taking down the entire system. So this could be killing one server at a time, or running experiments against one function at a time, or injecting failures into only a small percentage of requests, and doing them in only one region at a time as well. And you should also have a rollback plan ready, just in case things go bad, and you want to stop the experiment right away and then roll back whatever changes that's been done already. And last, but probably the most important thing is don't start in production. There's just so much you can learn by running experiments in a staging environment. And give yourself the time and the space to get used to the process of designing experiments or planning, executing them. And even the big boys, your Netflix and Uber and Amazon of this world, who are constantly running chaos experiments in production, they didn't start their experiments in production on day one either, and you shouldn't. And Russ Miles also talks about how chaos engineering is not just about stress testing your infrastructure. It can be applied to your entire stack that covers the people and processes that you have, your application, the platform, and the infrastructure that your platform runs on top of. If anything, the people and processes that you have are oftentimes the first thing that goes, judging by the number of post-mortem incident reports I've read that start with, operator did X, and then bad things happened. In fact, one of the most important lessons I learned from Russ is that when you're talking to the business, don't even use the word chaos. Again, it just puts the emphasis on the wrong things. And just as we just talked about, we want to make sure that our experiments are done in a controlled manner, and that is the exact opposite of chaos, right? So when you're talking to the business about what it is you're trying to do, call it what it actually is. Don't call it chaos engineering. Call it continuous resilience testing. And when you frame what you're trying to achieve in those words, it makes it easier for the business to get behind you, because I'm sure they share the common goal of wanting the system to be more resilient. When you mention the word chaos, it just freaks people out. They just think, oh, you just want to go ahead and break production. And that's not what we actually want. And in terms of the serverless paradigm and some of the tools that we currently have, there's a number of interesting challenges that has arisen with the serverless paradigm. So I mentioned Netflix's Simian Army tool earlier. Within that suite of tools, you have a latency monkey that can inject latency to simulate a slow response from an API call. And you also have Chaos Monkey that can kill each 2 instances randomly. You have also Chaos Gorilla that can kill an entire AWS availability zone. And finally, Chaos Con can just kill a whole region in AWS. And I've also seen several attempts at wrapping the logic of Chaos Monkey into a Lambda function so that you don't have to run and pay for server 24/7, just so that you can occasionally use it to kill other servers. But that's not what I'm interested in. I'm interested in how can I take the practices of chaos engineering and apply them to a paradigm where I don't have access to the servers that runs my code, and therefore there's no server that I can actually kill. But then chaos engineering is never about killing servers to begin with. Sure, it's what we do oftentimes to stress test the infrastructure when our application runs on servers that we have to manage and we can access. But chaos engineering is about identifying weaknesses before they manifest in system-wide aberrant behaviors. And we shouldn't confuse the principle of why we do something with the action that we do in order to apply those principles in our context. So having worked on several non-trivial serverless applications in the past, including migrating a social network to run pretty much entirely on serverless, one of the key lessons I've learned in that process is that there are just way more inherent chaos and complexity inside a serverless application. You have smaller units of deployment, which is great for many, many reasons that we're not going to go into in this session, but at the same time, you also end up with a lot more of them. And that means there are now more boundaries that you need to harden around. Instead of hardening your application around the application itself or the containers it runs on or the VM, now you have to harden the boundary for every single function that together makes up your application. And every function needs to be correctly configured and given the right IAM permissions, which is both an opportunity because now we have a more fine-grained control over every aspect of our application, especially from the security point of view, but it's also a risk because now there are more things that we need to configure and therefore more opportunities for misconfiguration, incorrect timeout settings for functions, or incorrect IAM permissions and so on. And people such as myself, who has been building things with serverless, we also just want to move away from having to manage and run servers at all. So you tend to find that we are using a lot of managed services with Lambda. And every single one of those services have got its own set of failure modes, some of which are documented, but many of which are not because they're tied to implementation details. And even those documented behaviors, that's probably not a good way for us to really verify their behavior until something bad actually happens. And then there's everything the platform does for you in terms of scheduling containers, scaling, polling kinesis, and then calling your function with the events, or retrying failed invocations. All of those features and capabilities have their own set of failure modes as well. And again, some of which may be documented, but many of which are not. And they are prone to change without notice anyway, because they're all platform-level implementation details. And oftentimes, when something does go wrong, we don't really have a meaningful alternative than to just wait for AWS to fix the problem, which, to their credit, they do a very good job. Compared to all the on-premises solutions I've seen in the past, they tend to recover from many issues a lot faster. That said, there are still plenty of weaknesses in my own code, and how my code deals with its dependencies, where I can use experiments to quickly identify weaknesses in those. For example, maybe I'm not handling timeouts when I'm talking to, say, third-party services properly, so that a slow response from a third-party system can actually cause my function to get timed out and by Lambda service, and in turn returns a 500 to my caller and and create a cascade failure in the whole code chain. Or maybe I'm missing some error handling in my code when I'm talking to third-party systems. In cases where if a dependency is not available, I could have returned with a cached response or maybe a static default value, or maybe I'm missing some of those default fallbacks. In cases where you have a multi-region setup, perhaps you're also missing a trick by not having regional failover as well. But by far, the most common issue of running into in production tends to be performance and latency related, and they can be symptomatic of a whole range of other underlying issues. It could be AWS having a networking problem. It could be you're talking to a server that is just overloaded or having very long garbage collection pause. And you tend to find a lot of the code there are you tend to find there are a lot of implicit assumptions about response time based on what we have experienced in the past. And we're not very good at thinking about those exceptional cases when, say, the response times start to deviate from the norm that we have seen with those services. And we can use latency injection to help us identify those weaknesses, to find those implicit assumptions that we have in our code. Using experiments, and again, following the simple 4 steps. Step 1, we need to know what normal looks like for our system. And what metrics we use to define that normality depends entirely on what type of system you're building. Some common candidates include your 95 or 99 percentile latencies or error counts. And if you're building a messaging-based system, maybe the backlog size is a good indicator that maybe you're falling behind. You might also use, instead of using absolute count, you might also use yield, which can be defined as the percentage of requests that you were able to respond to with a status code that's not 500. So once you've defined what normal looks like for your system, you can now start to design scenarios on how the system might fail given some failures that you can inject. In this case, there's some specific consideration we need to make for a serverless application. For example, even your Lambda functions can now run for 15 minutes now, but API Gateway has got a hard timeout of 29 seconds. So after 29 seconds, API Gateway is going to time out the request, even if your function is still running in the background. So your caller is going to get back a 500 response. And then there's the effect of cold starts. If you have one function talking to another via API Gateway, even if you know the timeout setting for the other function, by the time you consider the cold start time and whatever latency overhead API Gateway layer actually introduces, then the actual response time you can experience from the calling function can be a lot longer than a timeout on the other function. So you can't make hard assumptions about the maximum response time you can expect based on your knowledge about the timeout setting for the other function behind the API Gateway. And the rule of thumb in microservices is to use a short timeout, and that your timeout strategy should give your request the best chance to succeed, but not at the cost of waiting for so long that your function itself gets timed out before it hears back from the other service you're talking to, in which case you're going to end up creating cascade failures in your call chain. And this is where I find trying to pick the right timeout value is very tricky. When they're too short, you're not giving the request the best chance to succeed. So suppose I've got a function with 5 seconds left, and I set my timeout for all the outbound requests to 3 seconds, then even though I've got 5 seconds, I'm only making use of that 3 seconds. Or it can be too long. And so in the same example, my function's got 5 seconds left in invocation, but my timeout for the request is 6 seconds. So if the service I'm talking to having a really slow day, then my function is going to get timed out by Lambda before I hear back. And again, that turns into a 500 response to my caller. And this gets even worse when you consider that many of our functions do multiple API calls in one invocation. A simple example could be I make a call to DynamoDB, get some data back, mutate it somehow, and then make a put against DynamoDB to save the changes. And then I'm going to publish an event into a Kinesis stream to say, hey guys, some interesting event just happened. Maybe you're interested in that. And I see 2 common strategies on how to combat this situation. One is such that I've got a function with 6-second timeout, and I'm making 3 different API calls. So I'm going to divide my 6 seconds equally so that every request gets 2 seconds. And in this case, I can see that overall, we got enough time to make all 3 requests, but because one of the requests took longer than 2 seconds, it gets timed out. So we're not giving our request the best chance to succeed here. Another approach I see is I've got a function with 6 seconds. I'm going to be much more optimistic here, and I'm going to allow every request 5 seconds to complete. So even though individually, none of them took longer than 5 seconds, but collectively, they took too long and more than 6 seconds that I have in my function. In this case, my function gets timed out before I have the chance to do any recovery from those steps myself. So instead, my proposal here is to set your request timeout for those outbound communication dynamically based on the actual amount of invocation time you have left in the current invocation, which conveniently you can find from the context object that your function is invoked with. So in this case, I might say that for every invocation, I'm going to reserve some block of time at the end for recovery if things go bad. But before that, every request is given as much time as is left in the entire invocation minus the reserved time for recovery. And if collectively all the requests still took too long and I had to time out that last request, now I still have some time left at the end so that I can do some recovery steps, including logging the timeout incident with as much context as possible, including what was the API that I was trying to call, what's the timeout value, any correlation IDs that I've collected so far, as well as the request object and maybe something else as well. And I also want to record a custom metric for, say, servicex.timeout. In cases where I can't get the most up-to-date data from, say, DynamoDB, maybe I can return some cached value instead, and failing that, maybe I can return a static value that's been baked into my application. So that's actually a pattern that's baked right into the Historics library that Netflix published by Netflix, whereby you're writing your handlers into commands, and every command has got a fallback command if an error happens, and the fallback commands themselves can also have fallbacks and so on and so forth. So say you're doing a read from DynamoDB and that errors or timeout, then you can check, do I have local cache and stale value for this request? If I have, then great, I can return that, and failing that, I can return some default. And this is exactly what happens when you go to Netflix homepage, where they try to load your recommended movies. And if that API call fails, then they try to return a cache recommendation for you, and failing that, they also return just a static recommendation, which I think is movies from 1950s and 60s, where there's no copyright constraint. That's the important detail to consider. So here you're trading precision for availability, which is a good trade-off for many, many cases. But maybe you don't want to do that if, say, someone is checking their bank balance. Maybe you don't want to return a default value of 0, which of course is just going to freak them out, and they're going to call your customer support and scream at them, what have you guys done with my money? So even though this trade-off between precision for availability is great, you have to keep in mind that your user experience is the most important thing to keep in mind here. So next, let's talk about how can we then inject failures into our system, and specifically, or starting with, where do we do it? Suppose you've got a very simple setup here where you have a client application talking to 2 public-facing APIs, both with API Gateway and Lambda, both of which are talking to some internal API, which are also implemented with API Gateway and Lambda. And your hypothesis is such that one of those functions that are talking to the internal API is going to be fine when the internal API is having some issues and response time starts to spike. So in this case, you can simulate that by injecting latency delay into the HTTP client your function uses to talk to the internal API. This allows you to review any weaknesses you have in terms of how it handles slow responses from APIs that it depends on. And you should also do the same thing when you're talking to other third-party services, including those AWS services that we use all the time, like DynamoDB, or even other non-AWS services as well, like Twilio or Auth0 and so on. And we can apply the same technique for AWS DK by injecting some latency into the AWS DK clients. And we see an example of how you can do that later. And since we talked about how we need to worry about containment and blast radius. So for this particular experiment, the blast radius is fairly self-contained. It's just between the client and that particular Lambda function serving the endpoint that particular client is using at that moment in time. So you're not going to create cascade failures throughout the whole system. But what if you want to expand your hypothesis and say that, okay, the hypothesis that when the internal API is slow is not going to cause any problem in any of the public-facing APIs that depends on it, in which case you can also just inject latency into the invocation of a function directly, preferably through some middleware engine you use. For Node.js Lambda functions, there's a middleware engine that I find very useful, and you can use that to inject latency into an invocation. This has got the same impact as if you just inject latency into the HTTP client used by all the public-facing API functions. But your blast radius can be quite big now, because by injecting latency into this internal API function, you can impact all the functions that's on the public-facing side of things. And remember, the point is not to actually hurt production. So if you want to run these kind of experiments, definitely start in an environment away from production. And maybe you don't want to run these kind of experiments in production at all because of the risk involved. But at the same time, it's also very effective at finding and weeding out weaknesses very, very quickly. And I think you can actually use it for a different purpose as well. One of the common traps in software development I find is that we are not used to priming our developers to think about failures early on. This is especially true if you're working on a greenfield project whereby you're developing against a dev environment for months and maybe sometimes years at a time. And in that dev environment, you've got minimal load. You almost never see slow server response or errors. At the moment you release your code into production, that's a completely different ballgame altogether. And since we haven't been thinking about failures early during the development cycle, our system is not going to have a chance in production once it sees all the kind of different things that can happen in production. And in psychology, we have got this technique called priming, whereby we can subtly influence or manipulate the way that someone thinks and behaves by repeatedly projecting them with the same stimulus. And Facebook took advantage of this technique when they were moving into the Asia market where the network bandwidth is not very good. So they had this initiative called the 2G Tuesdays, whereby on every Tuesday, they toned the office Wi-Fi to mirror 2G bandwidth so that as a developer working on Facebook, I have a weekly reminder of what it is like to use Facebook on a 2G connection. So naturally, I start to optimize my code so that even on a 2G connection, I give my users a decent experience. So I think we can actually use failure injection to actually program our developers, our colleagues, to think about failures way, way, way earlier, by making our dev environments resemble the kind of turbulent condition that we should realistically expect our system to survive in production, by potentially making a small percentage of all requests have a slow response time or make them error. And of course, the client is just as important part of the whole system. In fact, it's your last chance, so it's your last line of defense before any cascade failures gets all the way to your users. And we should include our clients in our experiments as well. In this case, if I want to verify, I want to check that my clients are handling slow responses from the server properly and there are no implicit assumptions about server response time, then I can also inject latency into those public API functions directly. In terms of the blast radius, again, they're fairly self-contained. It's just between those individual functions and the client that's using them at that moment in time. So years ago, when I first started doing chaos engineering, and I was working on a MMORPG game, and we got this constant stream, like couple of complaints a day from user that says, "Oh, your app is crap. It just hangs when you try to start up and does nothing." And we couldn't, for the life of me, we couldn't reproduce the problem. And we added all these tests on a client, on a server, and still no luck. Until one day, I decided to take some of these things I've been learning about chaos engineering and started putting into practice. And we found that during startup, the client makes the multiple concurrent sets of requests. And if there's one specific API call to the server, that if you add the errors, or it takes more than 2 seconds, then the requests that are being made on parallel is going to fail with no reference pointer exception, and the whole thing just silently crashes. And that's why we had all these reports from the client. But it was such a complicated, there's a very specific step and something that for it to happen that we just couldn't replicate it in any of our tests and any of our attempts to reproduce the bug. But by making our dev environments resemble some of these conditions that we might see in production, we're able to start see those things happen, those errors happen in the dev environment. And like before, we can also inject latency into the HTTP client that our mobile or web client uses instead of injecting latency into the functions themselves. And whilst you're running the experiment, you're keeping your eye on the high-level dashboard to make sure that nothing really bad happens. And afterwards, you go through your metrics and try to find evidence that supports your original hypothesis. In terms of how do we then go ahead and inject latency into our code, if you're talking about static languages like C# or Java, then you can potentially use a weaver such as Post# for .NET or with ASP.J for JVM languages. And it's something that I used in the past, and I wrote a blog post about that a few years ago. And for Node.js or Python, other dynamic languages, you can potentially write wrapper libraries for your client. And as a proof of concept, I wrote a very simple HTTP client that allows me to pass in a config object that lets me toggle on and off those experiments, but also control how often we should inject latency and how much latency to inject. In this case, I'm just using Bluebird's delay function to then add some arbitrary delay to a HTTP request. So for the HTTP client itself, it's essentially just one big function that takes in an options object that allows me to pass in that config that we saw earlier, which ultimately comes in from SSM parameter store. I've got configuration in SSM parameter store, which in this particular experiment, I set the probability to 50%. Of a latency between 100 milliseconds and 5 seconds being added to a HTTP request my function. And since all my functions are hooked up to X-ray and instrumented, so in one experiment, I can see that there's no latency being added, so the whole request finished under 60 milliseconds. But on a different invocation, 3.4 seconds was added to this HTTP request. So that's all well and good for essentially a client library with just one method, one function. But that's not possible with the AWS CK, for example. It's not feasible for you to manually create client libraries for every single AWS CK client that you want to use. So in this case, you can apply the same technique, it's the same factory function as, say, Bluebird's Promisify_all. In this case, I've got a very simple module called the injectable, very bad name, but bear with me, whereby I can take an AWS client and override the get async functions with another to monkey patch the async function to take in another parameter, which includes the config value, the config object we saw earlier. And in this case, I can see that in one invocation, one experiment, 1.4 seconds was added to a request to DynamoDB get. So all that proof of concept is available on GitHub, so feel free to go play around with that and see what you can, if it's something that you can use. But we don't have to stop there. We don't have to stop at just adding latency and doing latency injection. We can also inject other forms of errors as well. For example, we can inject 500 responses to HTTP requests, but for specific AWS services, we can also inject those service-specific exceptions. DynamoDB's provision throughput exceed exception, for example, it catches me all the time because, again, it's not something that I see often during development, but in production, this kind of thing can happen all the time, very, very easily. And we're just not very good at thinking about those failure modes early on. And in the specific case of Lambda, you may also want to explore the scenarios whereby what happens, say, if a business critical function gets throttled because your overall concurrent executions has gone past the regional limit. What happens to the rest of the system? Say, for example, if something that is processing events from Kinesis and then synchronizing them to other systems, when that function keeps getting throttled because the overall concurrent executions has gone too high. As a simple hypothesis, you might say, okay, my functions are handling those HTTP errors properly, and we can simulate those failures. We can simulate those failures by, again, injecting errors into our HTTP client. And as we mentioned earlier, for specific AWS services, we can also, again, monkey patch the AWS SDK to then also inject service-specific errors as well. And if you want to simulate what happens if Lambda functions are being throttled, during an experiment, you can also then go to either programmatically or doing the console by setting the reserved concurrency for a function, which, given the name, actually means the opposite. When you set the reserved concurrency of function, you're setting the maximum number of concurrent executions that particular function can have. So if your function is running at, say, 10 concurrent executions steadily, you maybe want to see, okay, what happens if I set the reserved concurrency to 8 or 9, so that you now start to see throttling happening against that function to see how that impacts the rest of your system. Maybe that's where you can start to look at, okay, the backlog size has started to pile up, and that has got knock-on effects on other parts of the system, and the eventual consistency started to happen everywhere because we hadn't thought about what happens when the different systems that need to sync up together, and the thing that's doing that synchronization is now being throttled. So as a quick recap, failures are inevitable, regardless whether your code is running inside an EC2 VM, or inside a container, or inside a Lambda function. And the only way for us to truly know that our system is resilient against different forms of failures is to actually test it through the use of controlled experiments. And over time, as we do this, we can start to actually build confidence that our system would be fine. And the goal of doing chaos engineering is not to actually break your production environment, which is why containment and blast radius should be at all times front and center of your thinking. If you do jump the gun and go straight to production with a risky experiment and end up breaking the production environment, then you can be sure that no business is going to let you go back to production with your fancy chaos experiments ever again. And to execute the chaos experiments ourselves, we can follow 4 simple steps to define what steady state looks like for our system, hypothesize different scenarios and different failures and how our system should behave, go ahead and inject those failures into the system, and then keep an eye on the metrics and try to find evidence that supports our original hypothesis or to disprove it. And with serverless technologies like AWS Lambda, there are a lot more inherent complexity and chaos in the architecture. And if anything, there's even more need for us to use chaos engineering practices to identify those weaknesses early so that we can then go ahead and harden our applications and make them more resilient. And even without servers, you can still inject controlled failures into the system at the application level. By potentially injecting errors and latency into HTTP clients or into the AWS SDK our functions use, or into the functions themselves directly. And the client is also an important part of the whole system, and we should include them in our experiments as well. So with that, that's everything I have. I thank you very much for your time. And if you want to learn more about chaos engineering or general practice on how to make your server application more resilient, there's a couple more sessions tomorrow and the day after as well. So feel free to check those guys out. And please fill out the session survey in the mobile app afterwards as well. Thank you. If you've got any questions, I'm going to hang around here so you can come and ask me anything you want. Again, thank you guys very much for your time.